crash. And what happens is that it stores the information, and after the reboot, this will be queried by one of the launch daemons, and will read that and will dump it into a file on your file system on your iPhone. You can actually access that on a non-jailbroken device, first of all by going to the right menu, so you can just see it on your device itself. There's a menu for that. The other thing is you can, when you connect your device to, for example, Xcode on your Mac, then it will sync and download all this information, and then you can see it in your Xcode. And if you did not switch off all the don't send to Apple buttons, the next thing happens is that Apple fixed that vulnerability. So I'll never forget when you work on iOS kernel stuff to disable this sending to Apple. Or just make your whole network not being able to connect to Apple. Okay, so there's another way to get to this information. You can basically do the same way as Xcode by connecting your device to USB and then use something like libmobile device or the mobile device framework and just talk to the lockdown daemon directly with your own code and just pull out the panic dumps and all the crash dumps, and then you can make use of it. So what is such a panic dump? This is basically a text file, and it looks a lot like this. I used one of the new ones. So when you see here, this is from an iPhone 5S. Well, actually, I have a Zoom version of that. So you see the registers here. There are quite a lot of them. So this is not a normal ARM 32-bit device. This is a new iPhone 5S on an iOS 7.01. And this is obviously a kernel bug in iOS 7 that I triggered, and then this dump was generated, and in order to not give you the vulnerability, I basically X'd out all the endings, so you will not be able to find the actual code unless I forgot one important thing. In the beginning, when I did all this, I was like, oh no, I'm finished, and then I realized I didn't cross out the program counter, which was the most important one. So yeah, so now there should be no way to reveal what's going on. I even changed these small values to something completely random so that they wouldn't give anything away either. Because, you know, something like this happened a while ago. Some of the jailbreakers was recording a video of his new kernel exploit that he wanted to keep secret, posted the link to Twitter, and everybody could see the YouTube video, and then Comics was replying to that and saying, so why didn't you tell us directly that it was in like the serial driver? Because he could see the program counter at some point, and so he knew exactly that it was in the serial driver. Okay, so anyway, so the beginning of these panic dumps are actually just generic information that gives you like the timestamp when this crash happened, the version and the device model, and then you have all the registers. And later on in that dump you see some other information, like here you can see the exact kernel version string. So if someone gives you like a kernel panic dump, sometimes it's fake because they want to claim that they have like a bug. But here you can see if that doesn't match to the version number above, then there's a problem. You see the version of the boot ROM here, and you see, important here, you see the slide for the kernel address space layout randomization. So the first one is the actual slide value, and the second one is the actual load address of the kernel. So then, quite often you see the panicked task information here. So in this case, my iOS application was called Kernel Panic. And I started it just like, so it's like a kernel panic that you can trigger from within, yeah, you can trigger it from within the sandbox. So it's a very nice bug. In this case, you see the first one, I didn't X out the ending of that address just because this is like a heap address, so it doesn't give you any information. It's just like the task structure in the kernel heap. Yeah, so in this case, you see that in the end, there are some access missing, and the reason for that is that sometimes these panic dumps just are cut somewhere in the middle. So sometimes, depending on how the crash was, it doesn't even spit out the whole dump, so you are with incomplete information. And sometimes, depending on the bug, you don't get here these registers, so they are omitted from some of the panic dumps. So it always depends on the actual panic triggered, what information you get, and this is like the normal one. And sometimes, depending on the bug, you get even more information about the other kernel tasks running at the moment, and this gives you more information about what's happening right now. Anyway, so this was all like, I just see I'm already using too much time for this kind of thing. So basically it gives you all this information, but there are some problems with this debugging method. First of all, you have no memory content available. So you cannot see, for example, you see there was an access there, but you don't know why the access was there, and you have no stack dump, except for this little backtrace. You have no heap and no other information. Then you have the other problem on some devices like the iPad mini. Depending on the device, there's something broken, so like nearly always when you trigger a kernel panic, the kernel panic dump will just contain the name CRC error. Nothing else. And so you don't see what's happening. And sometimes, depending on how hard and where you crash the kernel, it's not even able to do the panic dump, so you will get no information. And sometimes there's like a problem where it crashes so hard that it always gives you back the old dump. So you do a kernel panic, a normal one, you get this, and then from that moment, every time you do a kernel panic, unless you use a different bug, you always get the old, like 2 days old maybe, kernel panic dump every time you reboot. It's not giving you the new crash, it's always giving you your old one. So this makes it very hard for working with that. And the other thing is, before iOS 5, or no, before iOS 6, this was one of the main ways people were actually using when they created jailbreaks, because they didn't have other facilities. Since iOS 6, we have all these kernel exploit mitigations, and this makes it a lot harder to just do an exploit with this information, so we need something new. So the new thing, or the better thing here is the KDP, the Kernel Debugger Protocol. And yeah, it would be very helpful to have this information, but like I said before, Apple doesn't want you to use that, so there's no way to access it directly, for example, from the iOS SDK. But when you look into the actual kernel, you will see that all these strings that you are used to from maybe the macOS X kernel, you will see that the KDP is actually in there, and you will see that all the boot arguments that control that, like debug, are also in there. So yeah, so there is a kernel debugger in there, and actually Apple tells me that they don't want to remove that, exactly for the reason that they sometimes get a factory device and they need to debug it on that device, so they need it in that kernel. And yeah, so long story short, we need several things to use that. We need a way to connect our device via serial to the Mac. We have the problem that KDPs, so we need a helper application. Normally we are not able to have these boot arguments, so that we cannot activate that kernel, this kernel debugger. So we either need to be able to give have some exploit to give it boot arguments, or we need a patched kernel to activate it later on. And there's another limitation. So far, no one managed to do this kind of kernel debugging on a device with the Lightning connector. Because when you look at the schematics of the actual iPhone 5 or 5S or so that leaked into the internet, you see that the chip, that serial chip that were used beforehand, it's disappeared from the schematics. So no one knows how this device still speaks serial, but most probably it does somehow. Okay, so in the old way it was very simple. You had this dock connector, and there's 30 pins, and 2 of these pins are basically serial. And then you could basically create your own cable. You had like a few ingredients, in total like 35 euro to build that cable. And well, you can see the slides later. So basically you attach all this stuff together, and in the end you have something that looks a lot like this. Actually, I have something like this in my room, so if you want, I can show you the real thing later. Okay, so and then you can just connect it to your iDevice, and this is the first part. The next thing is you need to download this driver, because otherwise your device cannot speak to the FTDI chip. Well, your Mac cannot speak to the FTDI chip. And once you install that driver, you can then use it. So now we are back, we have the device, we can connect it and everything. So now we have to basically activate the KDP on the phone. And for the old devices, for iOS 7, unfortunately there's only the iPhone 4 left. But for previously you had like a lot more devices that would work. So for these devices there's like this boot ROM exploit called LineRain, and you can use that to directly set the boot arguments with, for example, Red Snow or Open Snow or whatever you take to boot your kernel. And you can just say it, okay, debug equals 0x9, and then you activate the kernel debugger. And here in this table you can see basically what's happening here. So the first bit tells it that it needs to halt at the boot time. So the moment it starts, it immediately halts. And the other bit is basically enabling debug messages over the serial port. And you would basically do that on the command line with this command here. So you call Red Snow, you give it like an IPSW file, you give it the boot arguments, you tell it just boot, and a jailbroken kernel. So far so good. So then that's what you need to do to start the device. And then you would need a GDB, and the normal GDB on iOS, on macOS didn't have ARM support, but if you downloaded the iOS SDK, until very recently, like iOS 7, there was a GDB binary in the iOS SDK that gives you ARM support, also gives you KDP support and everything, but only over UDP. But the KDP that we can speak to the device is serial. So that's why we needed always a helper application, and this helper application is called Serial KDP Proxy. This was not originally written for the iPhone. This was actually written by this guy David Elliott, and he used it for real debugging of macOS X devices. But for some reason he needed a serial connection, not an Ethernet connection, so he wrote a little proxy, and that worked perfectly until macOS X Line, and then a lot of the ports that you will find on GitHub and different places, they stop working. So the moment you upgraded to macOS X Line, your code that worked perfectly before didn't work anymore. And this turned out to be a bug in that application. So if you want to get the latest or best version of that, just go to my GitHub, which is github/Stefan Esser. And there you find the one that actually works with the latest iOS versions. So once you have started that, you give it the actual name of the TTY device, the USB serial one that's registered by the FTDI driver, and then you are all set. Only problem here is that the serial connection with the cable is sometimes, depending on how you build the cable, a little unstable, so it could be that you have to restart this program over and over again because it loses the connection or the communication with the serial port. Actually, I haven't tried Maverick on my device yet, so I don't know if my NMI flag is. That the debugger is entered the moment you trigger an NMI on the device. And back in the days when we tried that on our jailbroken devices, if we triggered the NMI, then it would start dumping a panic to the serial, and then it would just reboot. And there was no entering the debugger. We never knew why. I only knew from the Apple guys, I knew that this was actually supposed to work because they used it, and they even told me how to use it, but it didn't work for some reason. We never knew why. Later, it suddenly started working with some tricks, which I will show you now. It's most probably, maybe they changed something in the kernel, or our kernel patches are better since the newer versions. Anyway, now we can basically make use of it. I'll tell you later how to trigger the NMI. So, okay, if you used the KDP before, you might have seen that it's quite problematic to actually use it, because if you stay inside GDB and you look around in the memory while you're connected, and you maybe need to go back to another computer, look something up in IDA, and you come back, most of the time your device will have rebooted. Or you just try to step through the code, and you step once, it's okay, you step twice, it's okay, you step the third time, and suddenly it reboots the device. So the reason for that was that there is like a watchdog timer in the back, and it realizes when the device is like unresponsive for a while, then it will just kill the connection, well, will reboot the device basically. And especially when we use that NMI feature, every time the watchdog will say there's something strange, and it would just reboot immediately. So I poked a little bit around in the kernel and realized that if you set one of these boot arguments, WDT, which most probably means watchdog timer, you set it to 0, or you use the serial command, which allows you to switch between different serial ports, then it somehow disables the watchdog timer, and from that moment KDP is a lot more stable and does not always immediately reboot. Again, KDP still, especially in comparison with, in usage with GDB, has a lot of other problems. So sometimes things just don't work, like breakpoints, they only work the first time, the second time they don't work anymore. So, but this most probably is one of the reasons GDB is really bad. And if you sniff the actual communication between GDB and KDP, which I'll tell you later, is you will see that even simple things like give me 40 bytes, GDB will turn that into 10 packets asking for 4 bytes each. So they will send 10 packets over the serial asking for 4 bytes every time. And other things like that. So GDB and KDP, they're not really like optimized to each other. Okay, so we now know how we make it more stable. Now I can tell you how this NMI works. So if you set one of these boot arguments, you can use, well, you can take your phone. Well, this is an old one, but it doesn't matter. So, and then you can trigger the NMI, which is a lot like a game console cheat code. So basically you have to press the power button and at the same time the volume down button, and for a few seconds. And if you do that for a few seconds and you're connected over serial and you have the debug boot argument also, then it will basically start to send over a panic log to the serial port, which we will see in the serial KDP proxy. And when it's finished with that, it waits for the debugger to connect. So from that moment, you can just connect with GDB and work with it. So why is that really good? Because previously, there were only one way to enter the debugger, no, 2 ways to enter the debugger. One way was to basically tell it, I want to break on the very first moment it boots. Then you could set some breakpoints and later on come back to GDB. And aside from that, there was only the other way, you crash the kernel and end up in a debugger. There was no way like, for example, now I want to suspend the kernel. Like, now I did something and I want to see what's happening, so now I want to suspend. There was no way to do that, but with the NMI you can basically do it anytime you want. Okay, so the next thing I want to talk about is PyKDP. So I already told you that GDB and KDP are not really tuned to each other, and sometimes when you use GDB with KDP, it lags really badly. So you step once, it's okay, you step twice, it's okay, and then you step again, and it takes like half a minute for this command to execute. Or you just do something and you next, and then you want to dump the registers, and again it takes like half a minute. So this is I don't know exactly why it's happening, but it's most probably due to how GDB is using KDP. And other things, if you just want to ask what is at this position in memory and things like that, doing this all with GDB is very painful, especially because the GDB that you have is a very old Apple GDB that doesn't have scripting support with Python or so. So you have a very old, very unpowerful GDB that doesn't give you scripting support. And yeah, also, like I said, Apple also removed GDB from iOS 7 SDK. So I started creating PyKDP. And PyKDP is basically a KDP implementation in Python. And it's, at the moment it only speaks KDP over UDP, so you still need that serial KDP proxy. Maybe in some future version I will directly let it speak serial, but it's not required at the moment. And this thing here now gives you access to basically, at the moment, only the most important KDP features, but in the future to all the KDP features. For example, access to physical memory is already possible, which is not that easy or not possible at all with GDB. Aside from that, yeah, you have all the normal features. You can attach and disconnect, you can read or write memory, you can just say, oh, now I set the breakpoints, please continue execution, you can read and write the registers, yeah, you can set and so on for the breakpoints. And there's, because it's just pure Python that speaks UDP over the sockets, there's no strange C bindings involved, so you don't have like to install a bunch of stuff to get it working. It's just like one Python file that you just include. And I will open source that. I wanted to do that during the conference, but I have to fix some bugs before I release it and do some actual documentation, because otherwise it's not useful. So I will release it most probably early November, like maybe if I manage to do it, maybe on the 1st of November, but I'm not sure. Maybe like the weekend afterwards. Okay, so how would you basically use that? Using it, it's very simple. For example, this is like an easy Hello World type example, where you just import the KDP module. You create your own object, you connect that object, well, you connect that KDP to the actual device. So this would now like wait until there's actually something connected to a serial that waits for the debugger. Then you ask, in this case, for the kernel base, which is one of the variables of that object that are automatically populated. So in the beginning, there's a few packets sent back and forth that do some kind of, what kind of device am I connected to, what are the features, what is the kernel version, and it also tells you what is the kernel ASLR slide. So these are like things that are auto-populated. And here, yeah, you would just calculate the kernel slide and just dump it to the screen so you know where the kernel is, just over this serial. And from here, of course, you can have like more complicated examples, like here, I'm just, now that I know where the kernel is, I just read 4096 bytes and then print them out, and I see this is basically the Mach-O header of the kernel, so you can basically read everything and from there do whatever you want. Or you can write to it and patch information, and especially when you connect early on, you have no problems with protections, so you would be able to write to that because there's no write only yet on this part of the code. Another thing you always want to do is, especially when you debug a crash, is you want to be able to dump the registers. This is also very easy. You just use the first CPU. Of course, on an old device there is only one CPU. You ask it for the thread state, which is at the moment the only thing supported, and it will give you back an array which contains all these informations here, all these elements here, and for printing out I just changed the last three names to something nicer. And then you see this are all the actual register values, and yeah, you see I didn't X out something here because that's not a bug, that's basically the initial start state. Yeah, in the end, there's a disconnect there. Yeah, and in the actual source distribution that I will then release, there are more examples like how to use breakpoints and everything, but that's not so interesting at the moment. So the next part I want to talk about is extending KDP. The problem here is the features that the kernel debugger provides you are very limited. So if you want more debugging features, you usually have to write them yourself and patch them into the kernel. And back in the days, people like Comex or me, we would do that by patching the system call table and add a new system call to the kernel, and then you would boot the modified kernel and use these system calls directly from our apps, so that we could do kernel debugging stuff like while we are basically exploiting. So I have, for example, kernels that I boot that give me read-write access and allocation access and deallocation access directly through an arbitrary system call. And now if I, for example, write an application, I can just use the system call during my exploit and just read and write something, test, for example, I have an assumption like this must be there in memory, I can just check that during my exploit. And later on, when I finalize my exploit, I just like comment all this stuff out and then everything is fine. Okay, so this has been done a lot of times, like Comex even released source code for that back in the iOS 4 days. So I wanted to do something new. So I wanted to, because I just invested time to create PyKDP, I wanted to add features to KDP so that I can use them remotely and I can Python them, I can script these features. So in order to do that, you have to look into the actual source code of XNew, which has the full, which is basically macOS X kernel, but is also very similar to the iOS kernel. So you see that in the source code, you see that KDP is basically handled by defining requests and responses, and all the requests and responses are going through a dispatch table. And the request handlers are very simple, you will see them on the next slide. And you can just modify or hook what's happening during the one request by just changing these entries in the table. And you might see, unfortunately I have no laser pointer, but you see there are some elements called unknown, so they are only partially used. Then others are just dummy implementations, so they are not giving any useful information, so you can just overwrite them. Especially if you know GDB and use them, so you know they are dummy anyway. For example, in iOS, the KDP_regions is just giving back one region which is static, which says I start at 0 and I'm 4 gigabytes big and I'm readable, writable, executable. So this is not useful information, so you can just reuse that slot, for example. Other things you could do if you want to reuse something, you have there readmem and writemem 64 and breakpoint 64 and so on. And you have the same without the 64, and the only difference here is that where they take an address and the parameters, they expect it to be a 64-bit or a 32-bit value, but they still work on the 32-bit processor if you use the 64-bit version. And if I'm not completely mistaken, GDB also only uses the 64-bit version, so the actual slots for the 32-bit versions are not used at all by anything, so you can rewrite them yourself. Yeah. So then the actual packets, like I said, they are sent over UDP, which is then sent over serial. And the actual packets all have a little header, which is 8 bytes. It contains like the information, what kind of request that is. It has one bit flag that says it's either request or reply. It has a very super secure 8-bit sequence number, but you don't really care because it's over serial, so you don't care. You have the length of the entire packet, including the header, and you have a session key. I have no idea what the session key is for, because I never needed it for anything, so there's no real need for it. And then each request is defined like this in the source code. You see the readmem request starts with a header, and then it has the address and the number of bytes that you want to read. And what you get in return is the header, an error, which is 0 if there was no error, and the actual data that is read from the memory. And when you look into the implementation of this, this is the readmem function. So all these packet handlers are looking very much the same. They get 3 input parameters. You have the pointer to the actual packet data, you have an in and out length pointer here, and you have the reply port, so this is where the answer is supposed to be sent to. And all these handlers basically first do some kind of input validation, so they actually check here that there's enough like data sent to basically have the right request. Then they rewrite the packet to make it a reply. They fix the size. Then they do some more input validation. Then they do the actual read, which is in a sub-function. Then they adjust the header line again because they now read data into the packet, so they have to tell it that's containing so much data. And then they fill out the reply port and fill out the actual length, and then it returns. So it's actually a very simple way to do that. So what we want to do now is we want to add new functionality. So let's add something new. We add a comment here that's just allowing us remotely to allocate memory. It's just an arbitrary example. You can do whatever you want there. For example, you could have something that gives you page table access. You could have something that gives you basically read and write access to the actual user space process that is running at the moment, because that is something that you cannot do with KDP normally. Yeah, and so in order to implement our feature, we just need these data structures. So we want to allocate something, so we have to tell it how many bytes. And the return, of course, we want to get the address that was allocated. So that's very simple. Then we can implement that, which will look like here. You see, we just return this here and everything is fine. Yeah, only one problem here. Because we add code to the kernel in an arbitrary position and we have no idea where we are, because we don't know yet what code we will overwrite or where we will put ourselves inside the kernel, and because we don't know the KSLR slide, all the access to global variables or to functions need to go through pointers in our code. So what I do here is I just define two dummy pointers, which I mark with specific values so that I can find them later in the binary. And the next thing you would do is you just take this and use your normal C compiler to, but tell it to not generate a binary, tell it to generate an assembly file. What will happen is it will spit out ARM assembly like this here, if you do it with a normal Xcode compiler. And you will see it defines a bunch of sections and then the code, and here's the data. Problem is, we want to have everything inside some place in the code or in a specific place in the kernel. So we want everything to be attached to each other, so nothing should be in a data segment. So the easiest way to do that is you just use a text editor and remove all the section comments, and you end up with something like this here. In our case, we only need read access to these pointers, which is fine. Because keep in mind, if we put that somewhere in the text segment, when you overwrite something in the text segment, you usually have no write access. So if you want to have write access to these variables, then you need to do a little more tricks. Then you maybe need to have, you need to have the data references in a different way. Okay, and once you do that, you can just use the AS assembler of the iOS 7 SDK. Just tell it to compile it, to assemble it. It will give you a Mach-O binary. You strip that binary to get rid of anything that's debug information. And then you can convert it into like a textual version of these binary things. Then you can remove all the headers and the footers. And what you end up with is like binary code in Python that contains the actual code the handler that you just created. Or you can use it any other way you want. The only problem here is on Linux or so, you would use the object dump, object copy binary for that. But on macOS, there is, as far as I know, there is nothing really good to simulate the same thing. So most of the time you have to do it manually or write your own code. So, and then you can put all that into a PyKDP script. See here we have the code, then we do our connection, we calculate some values. In this case they are hard-coded, but because you have read and write access you can basically find them in the kernel yourself, but here they are hard-coded. you attach the KLOC, the real KLOC address and the real KDP address to the end of the code, because that's where they were. And then you write the code into a specific target address. That, in this case, I just overwrite an unused function in the kernel. And then you write the into the actual dispatch table. We overwrite the readmem comment, because readmem is never used, because we always use the 64-bit version. We write it there, and then we call that readmem function 50 times. And the result of this is this here. So you see, you get a lot of allocations, and all these are kernel heap pointers, and like all 1536, which is exactly the amount we allocated here. And this is exactly the size of one of the KLOC zones, so that's why all of them are next to each other. Or there might be some in between that are not next to each other, but in general they should be next to each other. Okay, so before I run out of time, let's come to the last and maybe most powerful thing for kernel exploit developers. It's kernel heap recording and visualization. macOS and iOS both give you the opportunity to use debug boot arguments that are already existing in the kernel. They are, in this case, well, they're actually more, but these are the ones we use. We have the ZC, which activates zone logging in corruption mode. There's another mode for detecting leakage, but for our case, for exploit development, we are interested in corruption mode. We have a command called setlog, which allows us to specify one of the zone names. If you don't know what a zone is, just look up my slides from last year where I explained all the heap allocators, or the most important ones. So basically, let's say we have a zone that's called like this, so we can, from the debug boot arguments, we can tell it setlog equals this name here, and then we tell the kernel to log access to that zone. And we can tell it to use 8,000 records, which is the, I think, hard-coded maximum in the kernel. So if you boot your device now with these arguments, so what does it actually do? It will log all the allocations that happen and all the deallocations in that one zone and log them to a ring buffer that is 8,000 elements long. So if you have more than 8,000 allocations or deallocations, we're like, oh, well, you know, it's a ring buffer. So, and for every allocation, you get basically something like a timestamp, which doesn't really, it's not really a timestamp, it's like more a counter. You get the address that was either allocated or the one that was attempted to deallocate. And you get the last 15 elements of the backtrace. Okay. So how do you boot your device? Of course, you do it the same way as we did it before. Instead of debug, we now activate the actual zone logging, or we could do both at the same time. So we have the kernel debugger and the logging at the same time. Okay, you boot your device. What now? Actually, under normal circumstances, you shouldn't see any difference. Except maybe that your device is slower because more kernel memory was used, so your device has less memory, and so maybe something is slower. The interesting thing here is that Apple never thought about like implementing any feature to read that information that is now recorded into the kernel heap or data. Yes, if some of this is data and some kernel data and some of it is kernel heap. So all this recorded information is basically just there in the kernel, and there's some pointers pointing to it, but there's no feature actually to read it back. So you cannot access it from user space. So the only way to get to it is by, for example, patching in own features into the kernel, or for example using PyKDP and reading it from the kernel. Yeah. So depending on your actual current system, you either, your current, let's say, requirement, you can either do it really via PyKDP, or through the, well, you first have to do the NMI one, and then you can use PyKDP, or you have your own system call, and then you do it from within your exploit and check it. That's what my preferred version normally. Okay, so when you do that, you might have looked at the source code of XGNU, and you will realize the iOS kernel, the binary looks there like completely 100% different from what's in the source. And that's actually true. For some reason, the actual mountain lion heap logging and the iOS 6 heap logging are completely different. So in mountain lion, you have like just some simple pointers and simple allocations, buffers. But on iOS, you have like elements like this. Actually, they are very similar to those defined in the XGNU source code, but they are like switch around the position of some of the elements. But this one here actually doesn't exist in the XGNU source code. So this is all reversed. And what the interesting thing here is they have like a pre-logging hook and a post-logging hook, and they allow you to add extra hook data. But again, this is just like lying around in the kernel. There's no code making use of that. So there's not even like any driver or so making use of it. So you can just see that there's like this code there that's using it like this, but they're all null pointers. They're not used. Okay, and the rest of it is like, a lot of it is like just informational character, like how many elements there are, how long the maximum backtrace is, which you also cannot influence because it's hard-coded to 15, and like the size of one of these elements and so on. So what you need to do now is you do whatever you want inside the kernel, and you need to gather the data. Again, you can do that on the device with like an patched system call into the kernel, or you can do it via KDP remotely with PyKDP, for example, or with UGDB or whatever, and then you would dump it into a binary file. And in my case, I then convert the binary file to a JSON. Actually, I'm using a dirty PHP script for that. And it's not even Python. Maybe in a final version I make it Python script. And then you feed it to the visualization tool. The visualization tool is an attempt of mine to program something in JavaScript, which I would call desperately failed. Well, it works, but it's the worst code I have ever written. And before I will open source that, I have to completely clean that. And the nice thing here is it gives you an insight into a visual insight into the heap status in different moments in the timeline. I will show it you well, basically half-life. Yeah, it's really awesome during creating a kernel exploit because suddenly, for example, you don't understand why your exploit is not working, and you feed it to the heap visualization tool, and then you see, wait a second, why is there this block allocated that's not supposed to be there? And then while you see later, you can basically see who allocated it, and then you can yeah, change your kernel exploit. So basically, I will show it to you like live well, in the browser. So it will look like this here. And before I explain it, I will just show it to you. So this is like one of the possible test runs. Actually, the colors at the moment are given to the site every time you refresh the site by random, except the blue ones. They are fixed because the blue ones are the free list, the current heap free list. And the more light the blue is, the more it's in the front, so you also see the number. Down here is a 0, so this is the next element in the free list. And the more darker the blue gets, the more it's behind it in the free list. Aside from that, all the colors are assigned by random. And the only thing is, if it's the same color, that means the same code path inside the kernel allocated this. And then you can just hover over some of these, and you see the backtrace. And I even used a script from IDA to just export all the names to a JSON file. So this website takes this JSON file, so it has the symbols that you have, and then you can see exactly who allocated that block. in a different position it will be something different. Yeah, here for example you see there's a driver opened with service open extended and so on. And yeah, in other cases you will find different stuff like here for example this is the pipe system call and things like that. So you know, but this is not the only thing you can do. One thing that's currently broken is you can enter a regular expression up here, and then it will search from, well, before I explain you that, I have to show you the timeline. So you basically have a timeline here, you have a slider, so you can go back in time and see at what happened in the actual heap, and you see at what moment in time what was allocated. Yeah. So on. Oh, one thing I didn't tell you is, these blocks here that are like grayed out, those blocks are, because we only have like a rim buffer of 8,000 elements, we know that these blocks are actually used because we know that this page is used because we see other blocks in here. But during our 8,000 backlog, there's no action on these blocks. We only know that they must be allocated, but they are not touched in that time. So this is just dead. Yeah, so okay, so the idea of the regular expression that's not working at the moment correctly is you enter something and it will scan through all the backtraces and will put you will send you to the next moment in time. This string shows up in one of the backtraces. For example, you want to exploit POSIX spawn, so you would enter POSIX spawn up there, and then it will put you, bring you to the moment in the timeline POSIX spawn is actually used. This sometimes works, sometimes not. Because there's some strange bug. Like I said, this code is like really bad. Okay, so I have another example. Actually, because I don't know how much time I have left because my clock is gone. Okay, so this is another example. So for example, here you can see, well, actually you cannot because here you can see that it was a Mach message that used the open extended to open a driver, and this open driver passes the properties that you give it with OS unserialized XML, which is a function I discussed last year in Black Hat for heap feng shui. And then you can see that it uses the creates object like OS data, and OS data then uses kalloc, and kalloc uses setalloc, and then it allocates the memory. And then you can see that these here were allocable. I use in my iOS trainings to explain how you can still use OS unserialized XML. But I'm not showing it to you right now. I'm just showing you the last example, which was a hands-on test in my iOS security class. So this is like a logging in this case. Oh yeah, by the way, you always see the block size up there, so it's auto-guessing what the current block size is. In this case, it's 32 bytes zone. So you see there's a lot of allocations here. And the task was draw pictures with heap feng shui. And so here you can see the pictures. One time it's basically allocated, and we used a free list to draw a smiley, and one time we use a different allocation to fill this thing. Yeah, and like I said, this tool and the other thing with some basic documentation will be released early November for everyone to use it. And the last thing I want to say is that I'm working on an improvement, because as it is right now, it has a bunch of limitations. Right now it can only lock one kernel zone at a time, but during heap exploitation you often require to control several zones at the same time. So what I'm working on is like a kernel patch, very similar to the stuff I used like to patch new features in the KDP. So I patch a new system call in there that allows me to activate and deactivate my own kernel logging. And there are a few limitations I want to lift. For example, at the moment you have a backtrace of 15, which is most of the cases okay, but sometimes it's not good. And also there's some problems. The current logging sometimes returns dirty addresses. So there are some fields that are giving back completely strange pointers because they are leftovers from the last run. So I don't like that. So I will fix that for my own code. The limitation of 8,000 allocation deallocations normally, in most of the cases, is not a problem because you, when you try something, you are basically trying it right now and then you dump. So it should be in the last 8,000. But I will lift that too by having like a user space daemon just pulls all the information into user space all the time, so we are not wasting kernel memory. There are some zones, every time they run out of space, they grow not by one page at a time, but by multiple pages in a time. These are not a problem for the logging, but these zones are a problem for the visualization tool as it is right now. Because as you can see here, this visualization tool actually needs to know that this is all belonging to the same page or so. And if you have like a block that is bigger than a page, then it gets harder because from an address you cannot immediately see where a block is inside a page. So as long as you're inside a page, basically the address of the lower 12 bits basically tell you where exactly it is, or yeah. But if you have like bigger than one page, that it doesn't help you anymore. Yeah, and there's other stuff like right now my JavaScript needs to emulate the free list. The new tool will basically dump the free list so that you know the real free list. Yeah, there's something missing, like if you have an exploit on a new device, you also want to know what CPU thread and maybe other information like what kernel, what process allocated that memory, and this is all missing. So all this will be in the final version. And yeah, I will also release it, but it's most probably not being released anywhere before December or so. Oh yeah, and that were the questions. Yeah, any questions?
So just to clarify, Stefan, to get this working, you've got to use the LimeRain exploit through Redstone or the like on an older device?
Well, you can use LimeRain for the older device, or I'm not perfectly sure if they released it at the moment, but some guys wrote a tool that would, well, if you have like an actual jailbreak on iOS 6 with evasion, that tool would yeah, use the evasion security features that they basically give you. They would use this stuff to patch the kernel on the fly and activate the kernel debugger at runtime, which is a lot like what I presented last year at Kensec. So I discussed it in Kensec how you would what you need to do at runtime. So I'm not so sure if they actually released it yet. But still, even then, it would only work on devices that are already jailbroken. So it's like a chicken egg problem. You need like a vulnerability already working to activate the debugger.
So with the older devices in the LimeRain, you can use the more recent iOS versions?
Well, it works perfectly on 6.1 something. For iOS 7, you might need a different you might need a different tool, like OpenSnow or so. And even then you might need to patch it your own because the kernel patches OpenSnow applies are not that great. So I have my own patcher for that, and then, yeah.
Right.
Yep.
So what is the positive use of the exports? Or is it just to demonstrate it can be done? Or?
This here is just this was like how you would debug vulnerabilities to be able to write your own exploits. There's a lot of possible good uses for exploits on iDevices because imagine someone owns your iPhone. There's no way for you to find it out except you jailbreak it yourself. There's no way if there's someone smuggling code into your iDevice with like a private jailbreak. There's no way for you to detect it. There's absolutely no chance of you ever detecting that. So the only chance to do that is basically by having your own exploits. And then there are other users. Like I know of a company in China who basically creates hardware add-ons for iPhones, but these hardware add-ons only work with jailbroken devices, so that's why you also need to jailbreak. Yeah, there are actually companies that build a business on jailbroken devices. I don't know how intelligent that is, but yeah, they do that, and they obviously make money with it. And some of them do actually large donations back into the jailbreak community, to the actual jailbreak developers. Yeah, more questions. Then I'm...
Is Apple winning this?
What?
Is Apple winning this?
Apple winning? Okay. Well, I think the problem right now is that the pool of people that can do all this for free is getting smaller with every new iOS version. And the skill set inside that small pool is rather like fixed to some few heads. So maybe there are right now like 2 guys that are actually doing stuff, and at some point they most probably get an offer by some other company, and then they're gone too. And so far, everybody who wanted to get into that, maybe they succeeded, but they never made anything public. So those guys that actually do public stuff, they are getting smaller and smaller. They don't want to see the fact, but it's actually happening. You can see that. Every time they release a jailbreak, they create a new team, and every time the team gets smaller. And yeah, so is Apple winning? I don't know if they're actually winning, because there are like a lot of people doing that privately, selling to governments. And like, for example, when I killed that one POSIX spawn bug that turned out to be more than like an info leak, I heard that there were like 4 or 5 guys who were really pissed at me because they had this bug and most probably sold it to a government. So yeah, so you can see there's a lot of talent, and Apple is not winning. Apple, when you look at how they patch some stuff, it's like unbelievable. They patch only one code path to the same bug, or they don't see the bug that is right next to the other bug, and they only fix one of them, or maybe they see it but they don't close it.
So it's not Apple's winning, but maybe the open jailbreakers are losing.
Yeah, I would say Apple is not really winning. They just created like some mitigations now, which makes it a lot harder, and which even make the pool of people doing it publicly smaller. Because those that have the skills usually work in the industry, and they don't have time to give away hundreds of thousands of work hours or so for free.
The other thing with the
What?
with the you were saying before about that iPad mini, useless kernel pack.
Oh yeah.
What's your theory on that? Why is the mini different than the rest of the devices?
I have no idea. No one has an idea. It's just like the strange thing is I have personally seen kernel panics on my iPad mini, but at some point in time it just stopped working. So maybe there's a bug in the hardware, so that if you once trigger a certain condition, something breaks, and then there's because CRC error sounds like something is broken or so. So maybe there's some hardware element that's all broken in all the iPad minis. We will maybe see if there's like the new iPad minis when they come out, if they have the same problem or if the problem is gone. Because so far, oh, actually it's not true. If you search for the string CRC error in the internet, you will find at least one posting in some Apple forum where someone was using an iPhone 4S, I believe, had the same problem. So maybe there's really a hardware element that is maybe more vulnerable in the iPad mini than in other devices. But no one knows.
And are you going to keep at this?
What?
Are you going to keep at doing this?
Well, maybe for at least the next half a year or so. At some point I'm getting bored of this. And when you look at what Apple did, they did like a huge jump between iOS 5 and iOS 6. But when you now look at iOS 7, the jump is not that high anymore. They did something which will really make a lot of people angry, because they made the whole persistence game a lot harder now. And this is what all the government, them adding too many new mitigations in the future. And at some point it's just like breaking the same over and over again, and then it gets boring, and then I leave. Yeah. Yeah. More questions, or otherwise I believe there's a tea break that